Welcome back. This is what is this? This is section 8.2. In section 8.2, we're going to continue doing the kind of work we were doing in 8.1. We're going to talk about how to add up things where lots of things are happening and we can't just literally count them up. But this section, we're going to take a look at something called combinations, and that is our only objective in this section. So let's revisit an example from earlier. All right, so 25 entrants in an essay contest are being considered for scholarship prizes. The scholarships are going to be awarded to not the first, second, and third, but just the top 3 essays. In how many ways can the scholarships be awarded? Well, here's the major difference. We are still starting with a set. We're still starting with a big set in which there are 25 things. We still want to make a subset. We still want to pick just 3 of them. We still can't repeat because you can't be in the top 3 twice. There's no repeats. But what changed is order doesn't matter. And the reason why I'm saying order doesn't matter is because the way this problem is stated, you're going to get a scholarship if you're one of the top 3. So whether you're A, B, C for first, second, third, or B, A, C for first, second, third, or A, C, B or for first, second, third, for any of the ways that you can put those 3 letters in order, doesn't matter, because in all of those situations, those 3 people get a scholarship. Okay? So that makes this actually a combination rather than a permutation. Okay? And so we need a new formula. And so our new formula is right down here, and it says a combination is when a subset of R elements is chosen from a set of N elements. So there's our R element subset that we're choosing from a set of N elements, where the repetition of elements is not allowed, so we're not allowed to repeat, and the order is not important. Then C combination 25 choose 3 is going to be found by taking and doing this. So it's going to be the 25 factorial divided by 25 minus 3 factorial times 3 factorial. Now these actually, unlike permutations or distinguishable, could be done by hand, not too bad. Because this is going to be 25 times 24 times 23 times 22 factorial divided by 22 factorial times 3 times 2 times 1. And you see how this 22 factorial is going to cancel with that one? And we just end up with 25 times 24 times 23 divided by 6. And then we could say 6 goes in there once, goes in there 4 times, and then it's just 100 times 23, or 2300. So unlike the permutations, combinations much smaller, fewer number of these, easier to do by hand. But I still don't advocate doing them by hand because right below NPR, the permutations is the NCR, which is the combination. So I'm going to quit out of here because, of course, TI makes it slightly difficult for us, and so I can't type it in like that. I have to type it in like this, 25C3, so 25 math, PRB, and CR3. I type 3, and enter, and I get 2300. So there are 2,300 ways to pick 3 people from a group of 25 people to receive a scholarship. A combination. Okay. Here's some more examples. From a committee of 3 people, how many committees of 3 people can be formed from a group of 8 people? So I have a group 8. I'm making a subset of size 3. You can't repeat because once you're on there, you're on there. You can't be on there twice. And the order doesn't matter because it's a committee. We're not talking about, I don't want that. It's a committee. We're not talking about vice president, president, things like that. It's just you're either there or you're not. Order is unimportant. So that means I'm doing C, 8, 3. I'm not even going to use the formula. I'm not even going to go there. I'm just going to go straight to my calculator. 8 math probability NCR3, and I get 56. So there are 56 different ways to make a committee of 3 people from a group of 8 people. Now, one thing that I'm hoping you're noticing about section 8.1 and 8.2 is we're never actually finding out what those 56 things are. We're just saying there are 56 of them. We didn't find out what those 2,300 things were. We're just saying there are 2,300 of them. Okay. All right, let's take a look at another one. From a class of 15 students, a group of 3 or 4 must be selected or will be selected to work on a special project. In how many ways can a group of 3 or 4 students be selected? Well, I can't actually do this problem in one step. I'm actually going to have to do this problem in 2 steps. I'm going to have to find out all the 3 persons and all the 4 persons separately and then add them together. So I don't know what the answers are, but let's just make it stupid simple. Let's say there's 4 ways to do this and there's 6 ways to do this. That would mean that there are 10 ways total. I just need to find the 3-person ways, find the 4-person ways, and then add them together. I know it's not 4 and 6, so those numbers are way too small. Combinations are still pretty big. Okay? The 3-person is going to be C15, 3. The 4-person is going to be C15, 4, and I'm going to go to my calculator to figure these out. So 15, math, probability, NCR3, that's 455, and then I'll grab that command and just change that 3 to a 4 to do the other one. That's 1,365, and 1,365 plus 455 gives me 1,820. So there are 1,820 ways to select either a 3 or 4-person group of students to work on a special project. How about this one, bottom one here? In how many ways can a non-empty group of at most 3 lawyers be selected from a group of 30 lawyers? So I have a set. I want to create subsets. I can't repeat. Order doesn't matter because it's just putting them in the group, right? But what is this at most 3? Well, it's a non-empty group, so it could be a 1-person or a 2-person or a 3-person. So I'm going to have to do basically what I just did, but now do it for 1, and then do it for 2, and then do it for 3, and then add those things together, and that's going to give me my total number of ways to do it. This first one over here on the left is going to be a combination of 30, choose 1, and I happen to know that that's 30. This next one is going to be a combination of 30, choose 2. Let's see, I'm going to need my calculator for that. So that's going to be 30, math, PRB, 2, and that's going to give me 435, and this one's going to be a combination of 30, choose 3, so I'm just going to go grab that up there, change that 2 to a 3, and that's 4,060. And then I get the 4060 plus the 435 plus the 30, and I get there are 4,525 ways to do this. Okay? Now I hope you're kind of seeing where this is heading. At some point, we're going to start doing probability again. And we're going to say, what's the probability that there will be at most 3 lawyers? And then this is going to be our event. Right? What's the probability that it's 3 people or 4 people? And then this is going to be our event, our numerator. What's the probability that 3 people will be picked? And then this is going to be our event. That's going to be our numerator. Right? So we're going to have probability problems coming where these values that we're finding here are either going to be our events or possibly our sample spaces, and then we're going to put them either in the numerator or denominator of our fractions to calculate our probabilities. Right? So what we're looking at here is, how do I know what to do, when to do it? Right? Well, should I use a combination? Should I use a permutation? Or should I just multiply numbers together? Right? So if you have different options for selecting single sets of objects from a greater set, one question is repetition allowed? Okay. If repetition is allowed, then you're just using the multiplication principle. You're finding those M1, those M2, those M3s, and so on, and you're multiplying them together. If repetition is not allowed, if you're creating a subset where repetition is not allowed, remember this would not be a subset because repetition isn't allowed for in sets. Okay. So repetition is allowed? Nope. That means that we have to next ask, does the order matter? Because if the order matters, you're looking at a permutation and you use that NPR command on your calculator. And if order does not matter, then you're looking at a combination and it's going to be NCR. Right? So here I have a bunch of examples, in fact 4 of them, and we'll take a look. First one over here reads, how many different 4-digit codes are possible for an electronic home door lock with a 10-digit keypad? Well, I got 10 numbers to choose from, and I'm choosing, hold on, sorry about that. And I'm choosing 4 numbers. So is repetition allowed? Well, yeah, I can repeat. I can have a door code that repeats numbers, and if I can have a door code that repeats numbers, I'm just using the multiplication principle. And so then M1, the first number, is going to be 10. M2, the second number, I have still 10 choices. M3, the third number, I still have 10 choices. And M4, the fourth number, I have 10 choices. Now, it might not be very secure to use the same number 4 times, but I could. And then the multiplication principle says multiply those together, and 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. So there are 10,000 ways to do that. All right. All right, let's take a look at the next one. Let's see. A sample of 5 cans must be taken from a batch of 1,500 cans for quality control measures. How many samples are possible? Okay, I'm back up at the top here. Is repetition allowed? Well, it doesn't say anything about repetition, but I'm picking cans, so I can't pick the same can twice, so no repetition. Does order matter? No, it doesn't matter. I'm just putting 5 cans in a sample. Whether I pick it first or last, it's either in or not. So no. So I'm looking at a combination here. So I'm looking at a combination of 1,500, choose 5. So then I'm going to grab my calculator. 1500, math, probability, NCR5. Oh, that number. So let's see, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So let's see, that's hundreds, thousands, millions, billions, trillions, 62,860,358,440,000 different ways to do that. Right, moving right along. Let me erase so I can use my flow charty thing again. And how many ways can 15 math classes be assigned rooms in a building? Okay, repetition allowed. Well, no, because once I put a class in a room, I can't repeat it, so I'm a no. Does order matter? Yeah, because class 1 and room 1 is different from class 1 and room 2, so that makes it a permutation. So then it's going to be a permutation of, oh, it's all 15. So it's a permutation of 15 choose, or 15 permute 15. Calculator. I think this is going to be another big number. 15, math. Permutation, 15, and oh yeah, another big number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Scientific notation. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Hundreds, thousands, millions, billions, trillions. 1 trillion, 307 billion, 674 million, 1 billion, 307. No, 1 trillion, 307 billion. Gosh, this is a big number. 674,368,000 different ways to put 15 classes in rooms. All right. Arizona license plates are printed with 3 letters followed by 4 numbers. How many license plates are possible? Okay. All right, so back up to the top. Is repetition allowed? Well, I've seen lots of license plate with letters and numbers repeated, so I'm going to say yes. That means it's a multiplication principle, and so I got to figure it out. Let's see. M1 is going to be picking that first letter, so that's going to be a 26 because there's 26 letters in the alphabet. M2, second letter, 26. M3, third letter, that's also 26. I've got my letters done, now I've got 4 numbers. So M4 is going to be a number. There's 10 numbers to choose from. Remember, it's not 9, it's 10 because there's 0 through 9 digits. That's 10 numbers. M5 would be 10. M6 would be 10. And M7 would be 10. So in theory, this is how many they could make. It's 26 times 26 times 26 times 10 times 10 times 10 times 10. 26 times 26 times 26 is 17,576. So 17,576 with 4 zeros. 1, 2, 3, 4. So that means there are 175,760,000 different license plates that could be made. Now this is a big giant could. There's probably some of these that they won't make. If you use your imagination, think about a 3-letter word that they might not allow you to put on the license plate. I don't think there's anybody rolling around with, I don't know, God 111 on their license plate. I don't think they'll let someone have that one. Someone might be offended by it. So I'm going to argue that this number, while this is correct, is the theoretical number of license plates they could make. They probably could make less in reality. And that brings us to the end of section 8.2. One video, short section. Here's the big takeaway. This thing right here of when do I do, what do I do, and how do I know? What am I looking for? Is it a combination permutation or am I just multiplying? Look for repetition. And then once you've decided that repetition does or does not matter, does order matter? Combinations, permutations. Okay? All right, I'll see you all back here for the next video. That'd be what, section 8.3? Have a good one.